Hello, and welcome to History of Networking. Today, we're going to talk about the history of BGP. Joining us to share the details of the protocol that runs the internet is Tony Lee. Tony, why don't you introduce yourself and tell us what you're up to these days?
Hi, I'm Tony Lee. I helped build parts of the internet and helped get BGP deployed in its early days. I've done my time in computer networking and moved on to other things. So let's see, I guess the story with BGP really kind of starts all the way back in the ARPANET and the MILNET days. And probably the most important part starts off with the mail bridges, which were the boxes that interconnected the ARPANET and the MILNET. As you may recall, the ARPANET was net 10 and the MILNET was net 14. And if you wanted to send stuff between the two, well, you had to go through the mail bridges. And as a result, the mail bridges had to know about both networks. Now, that was good for two networks, but as we wanted to add more and more networks, the mail bridges needed more routing information. And we needed a mechanism to tell the mail bridges about this. So some folks over at BBN came up with a protocol called Exterior Gateway Protocol. And in particular, this is Eric Rosen's baby. And this was a distance vector protocol. And we started using it for connecting campuses onto the side of the ARPANET. And things got really confusing really, really quickly.
So Tony, when you say distance vector, people are going to think RIP. Is that close, or is it actually what we would really consider a distance vector protocol? I'm just curious because there is RIP really isn't. Okay, it is, but it isn't a true distance vector protocol, right?
Well, the BGP and RIP are so similar, it's not funny. They really are pushing around a hop count.
Okay.
And don't really have a good way of resolving loops. And BGP's updates are so slow that convergence was a major disaster. So loop freedom was a very, very large problem with BGP. We also had some major problems with the implementation of BGP where the mail bridges could actually only support so much stuff. As you might imagine, having one or two or even six routers in the middle of the entire internet who were trying to coordinate everything by themselves, and that was pretty much grounds for a scalability disaster. And we found those bounds pretty quickly.
Yeah. So in other words, the internet started out centralized. Sorry, I just had to throw that in there.
So as we started to dismantle the ARPANET and move to the NSFNet, it became very, very obvious that BGP was really not going to cut it. We were pasting things together by doing redistribution from this protocol into another protocol, and everybody doing their own thing, and none of it centrally coordinated. And we started having routing loops all over the place. And pretty quickly, we realized that this is not going to last for very much longer. So Kirk and Yakov sat down. This is Kirk Lougheed and Yakov Rector, and they should widely be proclaimed as the fathers of BGP. And they sat down one day and decided, here's what we really need. And they sat down with the now famous napkin, sketched out what they wanted. And
it was at a bar table in Washington, D.C. or something like that, right? Was it the D.C.? I don't remember. It was an IETF, right? It was like in D.C. or something. I don't remember exactly.
So they sketched out what they wanted and wrote down an RFC and then wrote some code to try it out. And it more or less worked. And after tinkering with it for a little while, they decided, well, there's some features in here that we just don't care about. For example, they had put in a notion of a directional topology. There was up and there was down.
Yeah, I remember seeing that. Yeah, that's kind of strange.
What does that mean? What does that mean?
Well, so their thought, the thinking was that the network was going to evolve into a hierarchy, right? Because that's where they were coming from. They had the ARPANET as the master backbone, and information would flow up to the ARPANET and then back down. Well, okay, in a generalized graph, that's not going to happen.
Yeah.
You're going to have an arbitrary topology. And so they realized that restriction really wasn't necessary. So they simplified the protocol and took all of that out. And as you see in BGP version 2, that's all gone.
So actually, one of the interesting things I found when I was looking at the RFCs was that in the early days of EGP and BGP, the drafts were only months from the RFC. I mean, like 1163, which obsoleted 1107, which 1107 is the first BGP, I think, that I could find, actual BGP RFC. 1163 was drafted in March and then RFC'd in June. Like 3 months later. Like, wow.
So it was very experimental, and nobody was going to argue very much about it because nobody saw it as seriously important. And back in those days, also, the RFCs really still were documents that were living documents open for comments. Right? So they didn't have much more status than an internet draft does today. So they were very flexible and easy to move quickly.
Yeah, how things have changed.
We have ossified.
Yes.
So let's see. BGP 2 had one bug in it, and that's the bug there is pretty simple. If two BGP speakers try to open TCP connections to each other simultaneously, you get confused. And BGP 3, all that does in there is to rectify that by adding a router ID and determining which of those two TCP connections to keep open and which to close.
Right. So master slave, basically.
Yep.
Okay.
Okay. So then my part of the story begins in 91 when I joined Cisco, and I got to help maintain Cisco's implementation of BGP. In particular, one of the early projects that I did was to actually implement the BGP 3 changes to Cisco's code in iOS Classic. And that got pushed out. And people were still playing around with BGP, but it really hadn't escaped the lab yet. And then the road conferences started happening, and this is in 92. And people realized that we had a scalability problem, and we decided to move to CIDR. And then the question is, how do we route CIDR prefixes? Because BGP can't support them at all.
Yeah. Actually, it was interesting because in November of 92 is the first draft I could find of BGP 4. And by the way, an interesting side effect of BGP 3 is, or interesting thing about BGP 3 is, I remember when I started Cisco in 96, there were still customers using BGP 3 live in their networks. Sure. On older routers. So BGP 3 was around for a very, very long time. People seem to think that things switch very quickly, but in reality, BGP 3 was out there for a long time that I could find. But anyway, so the interesting thing I found about BGP 4 was the first version I could find is 0.3. What's the story? I mean, where there's no 0.1 and 0.2, or I mean, you just decided to start at 3? Is that it, Tony, or you?
Actually, 0.1 and 0.2 out there. And there's some horrible mistakes in it, which is why we probably withdrew them and moved on.
Best lost to time, then, is what I'm hearing.
Yeah.
Mistakes were made. What can I say? So let's see. So early 91, 92, we spent a lot of time after we decided to move forward with BGP, spent a lot of time trying to get it deployed in the network. We started by deploying it using a series of tunnels, GRE tunnels, and built an overlay for passing around routing information.
See, the first routed overlay in the internet. Look at that. Lisp version 1. No, never mind.
So we had lots of scalability problems. The Cisco iOS implementation in particular was never structured to support the massive number of routes that we were shoving into it, 5,000, and it would fall over on a regular basis. Hey, this is...
And these were RISC processors, right? I mean, I don't remember what the processors were, but they were like really old 8-bit stuff.
It's not quite that bad. It was overall 68,000, running 16 megahertz with no MMU and 4 megabytes of RAM. And that includes
Wow.
okay. So we ended up playing lots of games to replace all of the internal data structures and change the algorithms so that they would scale. And then iOS's internal scheduling is all run to completion. So there's had to be some surgery there so that we could actually stop in halfway through a routing table scan. Otherwise, you would just hog the CPU for too long.
This is actually before interrupt level switching as well, right? And fast cache. So this is like even pre-AGS, or is that?
No. This is AGS, and there was fast switching at that point.
Okay.
But all of the fast switching, that fast switching cache was still a host route, a /32.
Right. Okay.
Okay. So if you got a cache hit on a prefix, it didn't help anything except the actual destination that you cached. So cache flushes were a nightmare.
Yeah.
So you had to be very careful and try not to trigger a cache flush. So it was interesting times, and we had to jury-rig a lot of things, and it was very messy. So with the adoption of CIDR, we decided that we had to move and distribute prefixes. At that point, Yakov and I produced the BGP4 initial specs. A lot of that was just stolen from stuff that he'd already done for IDRP, which is basically BGP translated into ISO. And then he brought it all back. And
nightmares. Tony's giving me nightmares tonight. Sorry.
Hey, it had to happen. So Yakov brought all of that technology back, and that became BGP4. Paul Trena took over Cisco's implementation, and he installed a more reasonable routing table that actually looked like a tree rather than the Cisco hash table. And the rest, as they say, is history. There were lots of bugs. There was lots of late night fixing. There were lots of times when we crashed the entire internet, and it was pretty painful. Fortunately, at the time, it was still an experimental network. Nobody was really, really expecting perfect uptime. And so when things went south, we got yelled at, but they didn't kill us.
Cool. So I see that 4271, I think, it still has your name on the top of it, right? You and Yakov, is that correct?
Sure.
Which obsoleted 1771. And I see that started in about 95, and it took until 2006 to get RFC'd. And the history page on that RFC is pretty incredible. Alex Zenin making all sorts of comments and all these people asking for changes. It was pretty radical, the amount of stuff that was going on there.
If you actually look at the net change, I mean, there were lots and lots of little good change, no question about it. But the fundamentals haven't changed all that much. A lot of the work that was done in 4271 was to help clarify the document, because frankly, we didn't do a wonderful job of producing the very clear document.
The Yakov rule of building RFCs, of building drafts. If you can actually read it and understand it, it's not written well enough yet.
That's not the intent. Actually, Yakov's rule, if a word is disputed, take it out.
Until you run out of words. So, yeah, pretty interesting.
So how much of the RFCs or work that you did was already done and then written, then you came back and wrote the RFC, or which way was it?
Well, so again, Yakov had taken BGP and roughly about BGP 3 and taken that to ISO. And because the NSAP addresses are variable length, it had to resolve all the interesting issues about doing a longest prefix match in IDPR or IDRP. And so all of that information was pretty well known. So when he brought that back, that actually preceded the coding. And so we just had to lift the stuff that he had decided. We did bash it around a bit to make sure that we wanted it to operate in the way it did. And then put it down in the RFC and coded to that. I can tell you one of the more interesting things. We spent a lot of time adding stuff to support deaggregation. And we were very concerned that we were going to have a lot of people trying to interrupt between BGP and EGP. And so we tried to make it work when you wanted to take all the classless prefixes out of BGP, deaggregate them into class full prefixes, and shove those into EGP. As it turns out, nobody actually used that feature, so that was a lot of work for nothing.
Yeah, reminds me of EIGRP AutoSummarization, right, on classful boundaries. And then immediately everybody turns it off because I've never seen an EIGRP network with it actually enabled. It's like, why would you do that?
Well, wasn't that, I mean, we're divergent in the EIGRP. That was a mistake based on a coding mistake that we should have turned it on by default, and we didn't, right?
No, it was actually on by default.
And
you have to turn, yeah. We should have left it off by default. Yeah, and everybody just turned it off. Yeah. So it's just one of those things, it's another instance of that. You really think this is going to be important. You spend a lot of time coding it, thinking through how to solve it. And in the end, when you actually get it in the field, it just really doesn't matter. Nobody cares. It's like, whatever. So
we were very concerned because we could see that if we didn't do it and needed it, we would be in a world of hurt. And
right.
Running and trying to do this under the gun, and that would have been really, really ugly. So in terms of an insurance policy, it wasn't a bad thing.
Yeah.
It would have been nice to know we weren't going to need it, but that's Monday morning quarterbacking.
Yeah. Sure. So I noticed that the early drafts were posted in the IWG working group. I don't remember the IWG working group ever existing. So like, when did the IWG to IDR thing happen? Do you remember? Was that like in the 90s or was that earlier?
That was earlier. I don't remember when that got changed.
Yeah, it's kind of weird because I just looked at the original drafts and they were like in this internet routing working group or something like that, IWG. And then, now clearly everything in BGP now is done in interdomain routing, which is IDR. And I was just trying to figure out what happened there. That's kind of weird.
I think that predicted.
So you said you had BGP2. What happened to BGP2? I mean, why'd you go from 2 to 3? You described 3 to 4 as a TCP open change, but what happened in there?
The TCP open change was 2 to 3.
2 to 3. So 3 to 4 was variable length encoding for CIDR.
That's right. And they're incompatible, so that was a big change.
Right. So did AFI's address families didn't come in until much later because of MPLS traffic engineering, right?
That's right.
Okay.
But we put AFIs into 4 because they were necessary inside of IDRP, and Yakov just brought them over and swore to us that we would need them, and he was right.
Yeah. So AFIs were a part, address families were a part of IDRP, and you just brought them into BGP4. Okay. I guess that would make sense for IDRP because, why would you have them? Because all you have is ISO addresses in ISO. Well, maybe X25, was that the thing? I don't know why you would, it would be a concern.
It was pretty obvious, at least as a Cisco employee, that having multi-protocol routing protocols was a good thing.
Yeah.
We already could do that with ISIS. We had multiple implementations of IGRP for XNS and for IP and for CLNS. We knew we were going to need that. And it made sense that we tried to make BGP more generic and so support multiple address families.
Yeah, so address families came in. That's kind of cool. Okay. So any thoughts on what's happened since then? I mean, there's all these update RFCs.
Well, as we were saying prior to starting the recording, BGP has become something of a dump truck.
It works, so we throw it all in there.
If people want to move information through the routing plane, they shove it into BGP. And it doesn't really belong there. And our grandchildren will hate us for doing that.
Tony has no opinions, by the way, Yvonne.
No.
So is any other were you going to ask something, Donald?
No, you were about to ask the same question, so go ahead.
No, I was just going to ask if there were any interesting stories around working with Yakov or anything like that, because Yakov is gone. I mean, I can't even find his email address anymore.
Oh, he's still around. I still hear from him.
So, I mean, any interesting stories about I know that when Scudder came in to Cisco, he was doing an implementation that was from, what was that little company? I can't remember.
No.
Yeah. And then there was that was that whole thing around calculating up to med and after med that he had done this whole mathematical thing around that never seemed to get implemented for XR type of stuff.
Mm-hmm. So when Yakov came in, let's see, one of the first things he got put on was to talk about tag switching, which had come from Ipsilon at the time. And certain people within Cisco saw that as a serious threat. And so Yakov started to poke around with that and try to understand it, and then started talking to many service providers, and that ended up becoming MPLS. And out of that quickly grew 2547 VPNs.
Right. Yeah, I remember the early tag switching images that we could run in the lab on 7200s.
Yeah.
Because you still had to software switch. There was no hardware platform support for MPLS for tag switching at that time. So you had to software switch everything. So you couldn't do it on some of the SSEs and stuff like that. You had to do it in software. So, you ran it on a 4500, whatever that high speed 4500 was in the 7200 and the 7200 BXR later, to get enough switching speed out of iOS to make it work. Yeah. So it's pretty interesting. So, yeah. Anyway, so that's cool. So any thoughts on implementation that was interesting? I mean, when you went through implementing it, I know most BGP implementations today have a kind of a common way that they suck updates in, they disperse them into a set of linked lists, doubly linked lists, and things like that. Is that something you originally started way back when you were working on BGP version 4 with Yakov? Is that the way you solved some of these problems, or is that?
Oh, no, that came much later. So the structure that I started with that was kind of handed to me as part of BGP version 2 was a hash table. And every route update had a version number. And the way you made forward progress to generate updates was to scan this internal rib and figure out what updates were greater than the last version number you sent out. And this, of course, became interesting when the updates became very large and you ran out of TCP buffer space, or you ran out of CPU time before you had to move on and do something else. So many of the hacks that I ended up doing were to figure out how to stop halfway through one of these scans and save enough state that you could resume and still generate correct information.
So that's the origin of BGP Scanner, which is the famous process that everyone who runs BGP hates.
Yeah, sorry. If you want to generate updates, that's how it had to happen.
So it was interesting that it was a hash table. And of course, over time, that became not tenable because the routing table grew from 5,000 routes, right? I mean, could say 5,000 routes forever.
I started at 5,000. I worked it all the way up till about 12,000. That was just natural growth at the time. And now, requirements have passed 5 million. So it had to change. It had to become more scalable. And a tree and linked list solutions and and what other folks have now called the transmission list are now de facto standards.
Yeah. So was update packing originally designed into BGP4? Or is that was something that was thought of at that time, or is that a later optimization that came in?
That was an optimization that we found very quickly while we were doing things. The storage requirements for all of the path attributes were very large. And so one of the things that I did in the early BGP implementation was to install a cache of sets of path attributes. And as soon as you have that cache, then update packing becomes much simpler.
Yeah.
You make sure that the set of path attributes matches the cache entry that you're using for this prefix, and if so, you can aggregate and add this prefix onto that bucket. So it's a relatively straightforward thing to do. And it was a huge, huge savings on memory, which was a really big concern at the time.
Yeah. And over time, of course, that cache became a linked list of its own, or a doubly linked list or whatever. We had Daniel on talking about the optimizations he did to BGP and how, he changed it from a single to a double linked list and this type of stuff to make it actually to get packing to be more effective. Because, of course, over time, as providers figure these things called communities out, they start using them.
Mm-hmm. Yep.
And then packing goes away because right. Now all of your attributes are different again.
Right. So you have to be very careful about what you actually do if you want to pack them.
Yeah.
And not packing has some implications for your bandwidth and your scanner.
Yeah. So interaction with TCP, was there stuff there that you had to do? I don't remember that there were any changes to TCP specifically, but I remember there were bits put in the code at various points to push, like say, okay, I'm done now, go ahead and send this segment. Was that done back then, or is that something that was later?
That was very old. We actually tried to create, rather than just use it as a pure byte stream, we actually tried to construct updates that were near correct segment sizes so that we would actually be reasonably efficient about using TCP buffers. The other big change that we actually did, of course, was the MD5 because getting security underneath us was key to avoiding the reset hacks.
Was that common in the old days?
Oh, yeah. Resets were happening all the time. So we had to do that MD5, and that happened in a real hurry.
Wow, I'm amazed by that. I mean, were people doing like multi-hop reset hacks? Is that what they were doing? Because that's kind of strange. Wow.
And,
the original DDoS. Not really a DDoS, the original DOS.
I can't help but wonder, I don't know if any perps that were actually caught, but I can't help wonder how many ISPs were attacking other ISPs.
Yeah, I'm sure. Yeah. I remember in the early days, there was this thing about, sending more specifics because you could capture more traffic, which would push people to actually upgrade your link instead of your competitor's link when people first started dual homing. That kind of thing. Intentionally de-aggregating because you wanted to capture more traffic to use up the links type of thing. That was those kinds of things were pretty strange, that type of stuff that was going on. So, yeah, cool. So I don't have any other questions really at this point. I'm kind of like.
Well, I just was wondering if, as you were developing BGP, did you have any concept of the scale of the protocol? Like what eventually it would be? I mean, because it's everywhere.
I wasn't worried about the scale. I was trying to make it till next week.
Here. Strategy I can understand.
But it is pretty.
Going to scale. We were, we watched the routing table growth, and that, you may recall back, Tony Bates was publishing weekly reports, and we were watching it. We were watching the plots go exponential, and we could see bad things happening, and there was a lot of worry at that time. And frankly, we haven't really done anything to fix that. We could easily see strange things happen with IPv6. So, millions and millions of prefixes are going to happen. And that's a really big concern.
It's actually not just that there's millions and millions of prefixes. It's that at some point you get large enough that it never converges. Just like today, it never converges. Because if you have, 5 million prefixes, the odds of at least one of them flapping any given tenth of a second is very, very high. It's the old MTBF. And if you get a large enough pool, the law of large numbers takes over and, you're going to have continuous flaps. So, how does that impact just rate of updates and things like that becomes a very major problem.
It is going to be a situation where you have continual flap, and that's most of it due to just normal link failure.
Right,
if you look at the number of fibers that we have in the internet right now and the failure rate of those fibers, you're absolutely right. The law of large numbers is going to kill you. So we have to accept that flap, and we have to engineer for it, and we have to be ready for it. Right?
Yeah.
Here's what the background churn rate is going to be. And by the way, if you have a really major event, you're going to spike well above that.
Yeah. Right. Yeah. And it's interesting that that's come up a couple of times. There was a whole knee in the fib thing that went on with the cost of memory and the fast cache and the Ceph table there for a while. And, I don't even want to talk about fast cache. I was in TAC when fast cache died, and it was just ugly. It was really ugly. But yeah, you still see that today, right? You still have, you still see things like this going on. You wonder, like we went through this whole thing with the cost of memory and having to re-optimize tables because things were just getting too expensive. The cache table, the memory to hold the cache was getting too expensive. You may remember that, Tony, that we went through that whole thing, right? And that big meeting in Washington or wherever it was, and we had all that discussion around it. But anyway, and you just wonder, it's going to happen again. It's got to happen again at some point. And
we have put in place no mechanisms anywhere that constrain the size of the global routing table.
Right. Yeah. Daniel did all that work, doing scripts and stuff to find out how much you could auto-aggregate. None of that's ever been deployed anywhere, as far as I know. Even something as simple as auto-aggregation would be very helpful. Jeff Houston does a thing. I don't know if you've seen that chart where he goes out and he talks about, he did a research paper, somebody did a research paper talking about the number of /24s in the V4 space that don't do anything. They don't make any difference in the routing of traffic. And yet they're still out there and they still flap. And it's just useless state that's doing nothing.
It's costing us CPU cycles and memory. So
yeah, that's exactly right. And if there's ever, like you said, a tremor or something else that happens, boom, it's going to blow up in our faces. But, well, now Yvonne's going to say, we've just scared the audience to death. They're all going to be sitting around.
Good. Maybe they'll do something.
Doomsday, BGP style.
They'll make a movie about it. So,
yeah.
Right.
So if you had a choice to go back and do something different, what would you do?
I would convince people that the way they were doing IPv6 was the wrong way.
We should do a show on that, Yvonne. IPv6 is an engineering lesson in bad engineering design.
Well, tell me more.
So, as you probably know, the IPv6 routing architecture is exactly the same as the IPv4 routing architecture, Xeroxed and quadrupled in size. And again, we've done nothing to constrain the way that people inject routes. We can play the same deaggregation games. And by the way, we've got a whole lot more bits to play with, so we can do a whole lot more deaggregation than we used to do.
Yeah. So the problem for me with deaggregation is this: it's a tragedy of the commons, right? Mm-hmm. I gain by deaggregating because I actually control my traffic inbound better, because MED is pretty much useless in BGP. Nobody even pays attention to MED, so whatever. So the only real hammer you have is the big hammer of deaggregation. So everybody uses the big hammer to do traffic engineering, but I gain from it. I actually gain financially from deaggregation, but it doesn't cost, it costs everybody else. I'm getting that gain at the cost of everyone else's memory and processing power.
Exactly
So,
right.
you know, I'm gaining and I'm putting the cost on somebody else. What's not to like?
And the same is also true for multi-homing.
Yep.
If I'm a multi-home site, I end up with multiple prefixes, I inject them, I get a benefit because now I've got robust connectivity and everybody else has to pay for my additional state. This is economically broken.
Yeah, that's right. So it's a very difficult problem to solve. And I don't know that there's the political will in any place to do anything about it until the thing falls apart.
It's sad to say it, but I think that there cannot be any motivation to fix it until there actually is a crisis.
Yeah, probably true.
Unfortunately true of human design throughout. This is just the way politics works. You don't fix things until they're near implosion. And this is true for Social Security. This is true for Medicare. This is true
for BGP. So were you involved in the original XR implementations, or was that all Scudder stuff?
I was not. I had left to go off to Juniper by then. The original implementation was something called DNA, and it did start while I was there, but I was not involved in it because I was still busy fixing other things. And then that eventually got renamed into XR and has slowly evolved. And at least as of 2013, actually worked reasonably well.
So did you actually do much of the same work at Juniper? Were you doing BGP at Juniper, or were you doing something different?
No, I ended up doing Juniper's first ISIS implementation.
Oh, it's your fault.
Oh, yeah.
I was just sitting here trolling through 10589 to write a statement of work. And I was thinking, I just so dislike 10589.
Really? 10589 is probably...
Which is ISIS, not BGP.
Yes,
right. That's probably the best protocol spec that's ever been written.
Oh, no.
Fighting words. So can we summarize by saying be a good internet citizen and summarize your routes?
Absolutely.
All right.
Yeah.
All right, guys. I think this has been a great conversation. We're going to start including, we'll include some details, some links to the RFCs in the show notes, but we really want to thank Tony for coming on and joining us. And
a picture of the napkin. A picture of the napkin.
I didn't know if the napkin was like for public consumption or not. But, yes. We can absolutely share a picture of the napkin. I don't know who owns the rights to that thing. I don't want to end up in a lawsuit.
It's an open napkin.
It's an open napkin. Open source napkin, yeah.
Got it.
You wipe your hands with it at Cisco still, too.
All right, guys. Thanks a lot. I think we'll wrap up this show. But again, we want to thank Tony for joining us and come back soon for more history of networking.
Yeah, thanks, Tony.
Thanks for having me.